Welcome to another installment of Math 1325. I can tell you're excited, right? This is related rates. So let's say a 26-foot ladder is placed up against a wall. If the top of the ladder up here is sliding down the wall at 2 feet per second, at what rate is the bottom of the ladder? Because as this starts to slide down, the bottom of the ladder is going to go away from the wall. When the bottom of the ladder is 10 feet away from the wall. So what rate? This is a related rate because we have the top of the ladder is certainly going to be related to the bottom of the ladder. Now, this goes back to when we were doing implicit differentiation. But now this section, everything is going to be with respect to time. So we can have many variables, but we will all find their derivative with respect to time. So let's let x equal the distance of the bottom of the ladder from the wall. Let y equal the distance of the top of the ladder from the ground. So these are moving at different rates. Notice that x and y are changing with respect to time. Also, if I notice here, I can see that this is a triangle. And remember the Pythagorean theorem? I can set this up as the Pythagorean theorem. And what I want to differentiate this is this x squared plus y squared equals 26 squared with respect to time. So the rate that the top of the ladder is moving down is my dy dt. The rate that the bottom of the ladder is moving away from the wall is my dx dt. And this is known as related rates, the change in x and the change in y. Okay, now that I got the dogs stopped barking, let's see what we can do with these related rates. So just like we did with implicit, we find the derivative of each one of these, but each one of them are going to have that implicit relationship with respect to time. So first, I found a relationship between these variables with the Pythagorean theorem. Now I take the derivative of each one with respect to time. Of course, the derivative of the constant is just 0. And then I plug in, well, there's some information that I was given. I was given that x is the ladder moving away, so I want to know when it's 10 feet away from the wall. I was also given the ladder sliding down, and notice it's negative because it's sliding down. And so now I can say, well, how could I find my actual y value? Well, I can take my x squared plus y squared. I can plug in my x value and solve for y. So I just go through all the steps. Of course, we don't do the plus or minus because my y is going to be positive. So I can now plug y in. I have everything I need. What I'm looking for is this rate here, that the ladder is moving away from the wall, and that's dx dt. So that's what I'm solving for. So I take this and I solve for dx dt. I multiply all that good stuff. I throw the 96 to the other side. I divide both sides by 20. And I get my actual rate at which the bottom of the ladder is moving away from the wall with respect to time. All right, so in this last example, we ended up using our equation in two ways. We used it first to find this relationship between the change in the top of the ladder and the change in the bottom of the ladder. And then second, we used it to actually find a value of y. These steps must be done in this order, okay? If you substitute x equals 10 and then you differentiate, you're not going to get the correct answer, okay? So just be careful of when you do a problem like this. How do you actually do these related problems? If it's something that sketching a figure will help, definitely do that. Find all the variables and the rates that are given and what we're actually looking for. Express all the rates, the given rates and rates to be found as derivatives with respect to time. find an equation that connects all these variables, implicitly differentiate the equation like we did, using the chain rule where appropriate. So that's where we had the add the dx dt, the dy dt, and then solve for the derivative that will give us the unknown rate. So these are the steps to help you become successful in how do you solve these type problems. A retail store estimates that weekly sales, S, and weekly advertising cost, X, both in dollars, are related by this equation. The current weekly advertising costs are $2,000, and these costs are increasing at the rate, so that's a derivative, at the rate of $300 per week. Find the current rate of change of sales. So I'm given these weekly sales, S, I'm given the cost for weekly advertising is X, and I'm given the current weekly advertising cost are $2,000 as well as a rate. So this is my change. It says these costs, my advertising, which is my X, change in my advertising over change in time is happening at this rate. So I start with the equation that they give me. I differentiate every one of these with respect to time. All I've done this piece here is the derivative of S would just be 1. So I just didn't put a 1 there. This, of course, is a constant, so the derivative would be 0 minus, notice these two pieces here are being multiplied, so I just brought the 40,000 out front. I took the derivative of e to the anything is e to the anything times the derivative of the anything. Okay, so in other words, that's the derivative of the exponent. And then my implicit part, my dx dt. And now I can make this look a little bit better. And I can say, well, they told me this rate, the dx dt, so I can simply plug it in and I can get my rate of sales. Let's look at another example. Suppose that a company's manufacturing flash drives, the cost, revenue, and we can find profit by revenue minus cost are given, where the production output in 1 week is X flash drives. If the production is increasing at the rate of 500 flash drives per week, when production is 2,000 flash drives, find the rate of increase in cost, revenue, and profit. So if you notice, you're working 3 different problems here. You're finding the rate of increase of cost, of revenue, and then of profit. So let's start with cost. I take my cost function, I take my derivatives with respect to time. If the production is increasing at the rate of 500 flash drives per week, in other words, that is my dx dt is 500, when production, which is my X, is 2,000, then I simply can plug in, I don't even have the variable my X, and so I plug in the 500, and this gives me my rate that cost is increasing. I do the same thing for my revenue. I set up my revenue, I find the derivative with respect to time. So that's what I've done here is I've taken my derivatives, all of these with respect to time. And now I can take the information that's been given to me and plug in my change in X over change in T, as well as my X is 2,000. And I get the rate that revenue is increasing. So this one we actually, the revenue cared about, the rate cared about how many of these flash drives I was producing. Let's do it again. Let's do it for profit. Well, you could go through all that mess again, right? Or you could just simply subtract. We said that with derivatives, you could subtract them, and this would be easy enough to find the rate that the profit is increasing.